This video is a review for Chapter 3.1 through Chapter 3.4. We look at three different types of lines, the first one being parallel lines. By definition, they are on the same plane and they do not intersect. These little arrows are used to indicate that two lines are parallel, and these double vertical lines are a symbol to say that A is parallel to B. On this cube, the red lines are parallel, the blue lines are parallel, and the green lines are parallel, among others. The second type of line, a skew line, has two rules also. They have to be on different planes, and they cannot intersect. So in an example like this, the red line here and the red line here, they're on different planes and they'll never cross each other. They are skew. But also, though these lines might look parallel at a glance, this line is on a different plane than this, and they will never intersect. So they are considered skew. The third type of line, a perpendicular line, these form 90-degree angles. There's this symbol here to say that A is perpendicular to B. It's kind of like an upside-down T. And then the square in the corner of an angle indicates that angle is 90 degrees. Perpendicular lines on this cube include the red here, the blue, and the green, among others. So there's four different kind of lines we're really looking at here. Parallel lines, they stay the same distance apart, they never cross. Intersecting lines will cross at one point. Perpendicular lines intersect and form right angles. And skew lines are on different planes and they don't intersect. Some of these properties can be applied to planes also. For example, this light blue plane is parallel with this other plane here, and this dark green plane is parallel with that plane. Or these two light blue planes are perpendicular. And remember that perpendicular planes will always intersect at a line. Next up we have the idea of a transversal, and this is a line that crosses two coplanar lines. So this blue line is a transversal. And when that occurs, these corresponding angles show up. A and B are corresponding angles based on their position relative to the transversal. Other labels that are created from using this transversal, we can see that A and B are considered alternate interior angles. Interior because they're between the two lines, alternate because they're on alternate sides. Then we have C and D here, which are consecutive interior angles, or we might call them same side interior angles. The exterior angles are outside of those two lines, and A and D are alternate exterior angles, and A and C are consecutive exterior angles. An important concept we'll use throughout this chapter is the idea from chapter 1 of vertical angles. These are angles opposite each other when two lines cross. These two blue angles, or the two yellow ones, are going to be equivalent. The other concept we use a lot is linear pair. These are adjacent angles that add up to 180. So A plus B equal 180. But what about when these two lines are parallel and they have this little marker here? Well, then these 8 angles that are formed, 1, 2, 3, 4, 5, 6, 7, 8, are all going to have certain types of relationships with each other. Either they're going to be congruent or supplementary, one of those two. If we think about vertical angles, 1 and 3 are vertical angles. They'll be congruent to each other. 5 and 7, also vertical angles, will be congruent. And because 1 and 5 correspond, and 3 and 7 correspond, if these two lines are parallel, all 1, 3, 5, and 7 will be the exact same measure. And the same is true for the vertical angles 2 and 4, and their corresponding pair 6 and 8. They're all going to be equal to each other. So another way to show that is that all of the black angles here are congruent to each other, and all of the red angles are congruent to each other. And the supplementary comes from when you combine any of the red angles with any of the black angles. So 1 and 2 add up to 180, but also 1 and 6, or 1 and 8. If we are given a diagram like this, we can fill in all 8 of the angles. 110 will show up here in the vertical angle spot, here where it's corresponding, and again with a vertical angle. To figure out the one next to it, I can take 180 minus 110, so I know that's going to be 70 degrees. Across the way is vertical. These correspond, and they're vertical. I might be given a diagram like this, where I have to solve for variables like x and y. And the first thing I would notice is that because 128 is down here, it corresponds and is up here. And I can set up this equation. 128 is equal to 2x plus 4. If I solve that, I get 62. I know that these two angles are supplementary, so I can take 180 minus 128, and I know that this angle here is going to be 52 degrees. So I can set this up as 52 is equal to 9y plus 7. If I subtract 7 from both sides, and I divide by 9, y is going to be equal to 5. Earlier in the video, we considered when these two lines that the transversal is crossing are parallel, all of these other angle relationships are true. Well, the same theorems work in reverse. Instead of saying, or just like we said before, if a transversal crosses parallel lines, then the corresponding angles are equal. We can work backwards and say if those corresponding angles are equal, then the lines must be parallel. That also worked for the alternate interior angles being equal, the alternate exterior angles being equal, or the consecutive interior angles being supplementary. If those angle relationships are true, then we can conclude that the lines themselves are parallel. Next, we looked at 3 different perpendicular theorems, and for all 3 of these, there were 2 if statements, and if they were both true, then we could form one conclusion. For the first diagram, if angle 1 and angle 2 are congruent to each other, and they form a linear pair when these two lines cross, the resulting conclusion is that A and B are perpendicular with each other. Since they have to add up to 180 and they're equal to each other, they're both 90. In the second diagram, if A and B are perpendicular, so this 90-degree angle is given, and we know that B and C are parallel, then it has to be the case that A and C are perpendicular, which kind of goes with our previous idea that if these lines are parallel, corresponding angles are equal. We're just being specific about how it affects perpendicular angles. The third diagram, we start with A and B being perpendicular, and A and C being perpendicular. So if these angles correspond, they're both 90 degrees, then I can conclude that the lines themselves must be parallel, and I could add these little lines here. Also in 3.4, we covered this idea of a perpendicular bisector. So back in chapter 1, a bisector is a line that divides a segment into 2 equal parts. So here, this line divides this segment into 2 equal parts. When we add the word perpendicular, that line has to form a 90-degree angle. That's the only difference. And it turns out for a triangle, if we're drawing a line from A to this opposite side, the shortest possible distance is using the perpendicular bisector. We can use that to write some inequalities. For example, if I know the perpendicular bisector is 7, and I know one of these exterior sides is x plus 3, I don't know exactly what x plus 3 is, but I know it has to be bigger than 7. So I can set up my inequality like so. And we know that x has to be bigger than 4 for this to be true.